Hey, I'm Alan Liu with Gnosis, and I will be talking with you today about conditional tokens. We'll be using Remix to explore the conditional tokens contract, and along the way I'll explain some of the design choices that were being made and what the conditional tokens allow you to do. First off, what are conditional tokens? There are some documentation on the conditional tokens available here at docs.gnosis.io/conditional tokens. Here you can find a number of pages that elaborate more on conditional tokens. In a nutshell, conditional tokens enable prediction markets. Prediction markets are markets about the outcome of any future event. They allow agents to aggregate beliefs about the future. In addition to this, conditional tokens also enable combinatorial prediction markets. These are prediction markets with a deeper structure than what one might typically encounter as prediction markets. There are many use cases that are enabled by conditional tokens, but today we'll only be exploring the basic mechanics around the conditional tokens. If you'd like more information, please consult the docs. We will, however, also be making use of the developer guide, which you may find by clicking on the documentation tab on the docs page. Today we'll also be using Remix to do some live development. Remix is a browser-based integrated development environment tailored for Ethereum development. You can find it at remix.ethereum.org. For purposes of this guide, we'll also be using a gist that I've created. The link to the gist will be posted below, so please follow along using this link. To begin, we will import from a GitHub gist. Importing this gist will result in 3 files being imported into your Remix IDE. Let's take a look at the files. First, CT helpers is a library which implements helper routines for the conditional tokens contract. We won't be going too much into detail about the implementations done here, but this is required by the conditional tokens contract. The conditional tokens contract here is actually adapted from the canonical version to use OpenZeppelin's new ERC 1155 implementation. For this reason, it actually differs from the canonical version by a little bit. For instance, the Solidity version used to compile this was 0.5.10. However, this source file has been adapted to be compiled with Solidity 0.6. Also note that there are methods available on this particular version of the conditional tokens that isn't available on the canonical versions. The methods I am speaking about pertain to the metadata URI introspection methods. This is an optional extension of the ERC 1155 standard, which is implemented in OpenZeppelin's implementation of ERC 1155. For this reason, a constructor not present in the original source is included here. Finally, the gist contains a tutorial.so source file. This source file imports the conditional tokens contract as well as an ERC20 base contract from OpenZeppelin. This base contract is used to implement a toy token. This toy token we'll be using to explore the mechanics of the conditional tokens. Note that there is a public mint function that allows any account to mint any amount of this toy token for any other amount. This toy token is not meant to be used in production, but will instead illuminate the way in which ERC20 tokens interact with conditional tokens. Once you have imported the gist, go to the Solidity compiler. The Solidity compiler should be used to compile the tutorial.sol source file. Here I am using 0.6.6 and I am enabling optimization. However, this should work with any Solidity 0.6 compiler. Once you've compiled the tutorial, go to the Deploy and Run Transactions tab. We will be using the JavaScript VM in this tutorial. However, if you'd like, you can follow along on Rinkeby or even mainnet. The canonical addresses for the Rinkeby and mainnet instances are included on the conditional tokens source file. However, they do contain small differences that have been hinted at earlier. Let's begin by creating a couple of ERC20 toy tokens. We'll deploy a couple of toy tokens in order to illustrate how different ERC20 tokens can be used with the same conditional tokens contracts. You should see the two toy token instances under your deployed contracts list inside of the Deploy and Run Transactions side panel. Note that these toy tokens have different addresses on the local JavaScript VM. Now that we have a couple of ERC20 tokens on the chain, let's deploy an instance of the conditional tokens. We will only need one of these instances. You may need to increase the gas limit. Here I've increased the gas limit to 6 millionth. The conditional tokens is a pretty big contract. Taking a look at the conditional tokens contract interface, we can see a number of methods that we can call to make transactions, as well as a number of methods we can use to query the state of the contract. Here I would like to note that the method URI is not available on the conditional tokens. This is because the URI method is part of the optional ERC 1155 metadata URI extension, which is not implemented on the canonical conditional tokens instance. So we will just ignore this, even though we can call this on the conditional tokens contract instance that we have deployed here. The rest of the methods, however, do exist on chain and work more or less the same as they would here. Our first topic when discussing the conditional tokens is the concept of a condition. A condition can be thought of as a question that an oracle is expected to give an answer to in the future. On the conditional tokens contract, conditions are represented by 3 parameters: an oracle, a question ID, and an outcome slot count. An oracle is just the address of an Ethereum account. That account is expected to make a transaction to the conditional tokens in the future, reporting the result of a condition. The second parameter is the question ID, which is used to identify the details of the question. Here the contract has no knowledge of how to interpret the question ID, and it is just used as an input for distinguishing different conditions. However, many front ends choose to interpret the question ID in very specific ways. For example, one may have a database where entries of the database may be identified by this question ID. Finally, we have an unsigned integer parameter called the outcome slot count. This outcome slot count is a count of the number of outcome slots there are associated with a condition. Outcome slots can roughly be thought of as the number of different outcomes for the question of a condition. We will return to explain outcome slots more fully in detail later. First, let us get a condition ID. First, we'll pick one of the accounts we have at our disposal to be the Oracle account. Note that I'm switching back to the original account, even though I have designated a different Oracle for the condition. We'll get the condition ID for a condition where this Oracle reports the result for a question with this ID. And finally, let's say this condition has 3 outcome slots. For these parameters, we can use getConditionID on the contract in order to derive an ID for the condition. This ID can be used to query the state of this condition on this contract. If we enter this condition ID into the getOutcomeSlot accessor on this contract, we'll see that the contract reports back a value of 0. This is because this condition has not been prepared yet, so the conditional tokens contract is not aware of the existence of this condition. In order to prepare this condition, use the parameters that we've passed into getConditionID, which are the Oracle account, the question ID, and the outcome slot count. Use these parameters and make a prepare condition transaction. Note that the account actually preparing the condition does not have to be the same as the Oracle account. Here I am going to use a different account to illustrate this. Once the prepare condition transaction has been mined, the state of the contract will be updated. Checking getOutcomeSlot on the contract will now return the correct outcome slot count. Let's prepare another condition with a different Oracle account and a different question ID. And finally, 2 outcome slots. Be sure to make note of the correct condition ID. For those of you who know a bit more about how the Ethereum virtual machine works, these arguments are packed together and hashed by the Kekak256 hash to generate the condition ID. Next, in order to proceed, we have to talk about bit arrays. Bit arrays are exactly how they sound. They're just an array of bits. In fact, you can think of your hard drive as one huge bit array. They're useful for indicating whether something is included in a set or not. One way to represent bit arrays is with unsigned integers. To demonstrate this, I'll use the JavaScript console. Now, those of you with a bit of programming experience may already know about the phenomenon of integer flags. This is exactly that. For those of you who don't know what I'm talking about, let's talk about numbers. The way most of us learn about numbers is by counting them with our hands. Now, most of us probably have 10 fingers. So when we count in tens. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. However, this is not the only way to count. Computers count in binary. What this means is they count as if they only had 2 fingers. You can see this in action by using a binary number literal. To create a binary number literal in JavaScript and in many other languages, simply prefix 0b to your string of ones and zeros. For example, 1 is still 1, however 2 is now written with 1 0. 3 is written as 1 1, 4 is written as 1 0 0, 5 is written as 1 0 1, and so on and so forth. This actually reflects how the computer is storing numbers on its system. In addition to this, there are many operations that operate on the bit-by-bit level. Here I want to note a way that you can look at numbers in binary. If you have a JavaScript number, you can actually find its binary representation using toString, passing in 2 in order to indicate that the number should be cast to a string representation of the number that is in binary. Let's use this to explore bitwise operations. You can use this to see how bitwise operations affect numbers. For example, a bitwise AND will only allow the bits that both values share in their respective places. A bitwise OR will have a bit switched on in every place that is switched on in either value. And a bitwise exclusive OR, or a symmetric difference, will leave a bit on only if exactly one of the bits are on in both values. The point of this is to illustrate that representing an array of bits as a number is a very efficient way of doing so. With this, we can turn the native 256-bit unsigned integers in Ethereum to 256-bit long bit arrays. So now that we have a conception of what a bit array is, we can now talk about index sets and outcome collections. I mentioned earlier that bit arrays can be used to represent inclusion inside of a set. So let's say a condition has 3 outcomes. You can number these outcomes with indices starting from 0. So the first outcome has index 0, the second outcome has index 1, and the third outcome has index 2. An index set for these outcomes would be a bit array with 3 bits. The lowest bit, or the bit in the ones place, would represent whether or not the index 0 is in the set, being represented by the index set. Similarly, whether or not a bit is set in the 2's place would indicate whether the index 1 is included in the set or not, and the bit set in the 4's place would indicate whether the index 2 is in the set or not. Let's consider the first condition that we had prepared, a condition with 3 outcome slots. Its condition ID is highlighted here and essentially represents the condition inside of the conditional tokens contract. This condition, together with another parameter called the index set, specifies an outcome collection. Let's give the outcome slots for this condition colloquial names to ease the discussion a bit. We will call the outcome slots for this first condition A, B, and C. For example, in order to determine the index set of an outcome collection containing outcome slots B and C, first list the outcome slots in order. Here I've written 0 for A, 1 for B, and 1 for C, in order to indicate that A is not included in this outcome collection, while B and C are. To turn this array of bits into a uint, we will start counting from the least significant bit. Basically, take 0, 1, 1, write it backwards and put 0b in front of it. As you can see, in the ones place corresponding to index 0, or the first outcome slot, there is a 0, while in the 2s and 4s place, there are 1s, which correspond to the second and third outcome slots being inside of the collection. We can also recognize this integer as the integer 6. What this means is that the outcome collection containing B and C, which represents the outcome in which either B or C occurs, can be derived from the condition ID and the index set, here written in normal decimal notation. The ID for this outcome collection can also be derived. In order to get the collection ID for this outcome collection, supply the condition ID and the index set for the collection to the getCollectionID method on the contract. Taking a look at the getCollectionID parameters, you can see that there are actually 3 parameters that are expected by this method: a parent collection ID, a condition ID, and an index set. For now, we will supply a value of all zeros as the parent collection ID. And as mentioned earlier, we will now also pass in the condition ID and the index set. The contract will calculate a collection ID from these parameters. Please note that this collection ID is different from the condition ID, and that represents a collection of outcome slots on a specific condition. Let us make note of this collection ID for the future. We may do a similar thing for an outcome collection containing only one outcome slot, for example, the outcome slot A. The index set associated with the outcome collection with only the outcome slot A can be found to be the integer 1. Like before, we will use getCollectionID in order to get the collection ID associated with this outcome collection, passing in 0 as the parent collection ID. Similarly, for the second condition that we have prepared, for the purposes of this guide, I will give this condition's outcome slots names as well. I will call the first outcome slot low and the second outcome slot high. And I will consider 2 outcome collections based off of this condition: the outcome collection with only low and the outcome collection with only high. The index set associated with the outcome collection with only low is 1, while the index set associated with the outcome collection with only high is 2. Note that while the outcome collection of only low may have the same index set as the outcome collection for only A, it differs in the condition that is also used to derive this outcome collection. In this case, the condition is the second condition that we have prepared originally. And in the same manner as before, we can derive the IDs for these outcome collections. Again, when using the getCollectionID method to derive these collection IDs, pass in 0 as the parent collection ID. Having discussed outcome collections and how to derive their IDs, we can now finally get to a concept called positions and their respective IDs. Positions can simply be defined as an outcome collection together with a collateral token. Recall earlier that we had deployed 2 ERC20 tokens on the virtual machine to be used as collateral. The addresses for these tokens can be found earlier in the deployed contracts list. To help differentiate these tokens, I will give the first token a name of T1 and the second token a name of T2. A position that results in the payout of token T1 under the condition that either B or C from the first condition occurs can be derived from the T1 token address on the chain and the B or C collection ID, which we have derived earlier. This position, token 1, when B or C occurs, has a position ID that we can find using getPositionID. GetPositionID takes the collateral token address, or the address of T1, and the ID of the outcome collection, and returns an unsigned integer as the position ID for T1 when B or C occurs. This position ID is also the ERC1155 ID that identifies the unique conditional token or outcome token that represents a stake in this position. We can also find the position ID for a position that pays out in T1 when only A occurs by using the same collateral token address, but the collection ID for the outcome collection of only A. We can also find the position ID for the outcome collection B or C, except one that pays out in T2 instead of T1. Note that this position's ID differs from the other position's ID that pays out under the same circumstances except with a different collateral token. We can continue to derive position IDs in this way for the other outcome collections mentioned earlier. Once we have these position IDs, we can finally start querying accounts for their respective stakes and positions, or the amount of conditional tokens they may be holding. In order to do so, we may use the ERC1155 method of balance of, or if we are querying for multiple positions, balance of batch. Even though the position IDs that we have derived do represent these positions, and we have prepared the conditions behind these positions, there isn't any value at stake yet. In fact, the toy tokens that we've been referring to here haven't even got a supply. So if you look at the total supply for these toy tokens, you'll see that they're 0 because no account has any. And this means that on this chain there isn't any conditional tokens that exist yet, and so if we try to query an account's balance, we will find that they are 0 right now. So let's just try it with the first account in the dropdown and the token 1 under a condition that B or C occurs, that position. And we see that the primary account has no such conditional tokens with this position. So you may wonder, how do we create conditional tokens and how do we get accounts to have a stake in positions or have accounts hold conditional tokens? We can do this using an operation called split position, available on the conditional tokens contract. The split position method is pretty complicated, so I'll walk through the individual parameters of this method. First, we have the collateral token. The collateral token parameter is the address of the token that will be backing the positions that we will be generating conditional tokens for. Before any tokens can be created on the conditional tokens contract, however, the corresponding collateral token for a position has to be sent to the contract for the conditional tokens to hold as collateral for the position. We'll begin by creating some T1 tokens. So we'll just transact with the first account here and use the mint function on the first token, or the T1 token, in order to mint this account some amount of token T1. And say we'll give the first account 100 units of T1. You can double check that now the first account has a balance of 100 units of token T1. Note also that this is a completely different token from the second token. So if we query the same account for its holdings of T2, we'll find that there isn't any that holds. Now during the split position transaction, the contract will actually attempt to transfer an amount of T1 to the conditional tokens contract. What this means is that before the split position transaction can be made, the account which is calling split position must first approve the conditional tokens contract and allowance to be used by the conditional tokens. That way, when the request to split position hits the conditional tokens can verify the transfer of the collateral token to itself while doing the position splitting, thereby ensuring that it actually has collateral to back the conditional tokens that it will mint in the split position operation. In order to do the approval operation, we need to get the address of the conditional tokens and make sure the conditional tokens can spend all 100 of the tokens that we've just minted. So now the allowance of the conditional tokens that the primary account has given it is 100. Looking at split position again, we will first give the T1 token as the collateral token. For the parent collection ID, similar to the call to get collection ID, we will be using a 32-byte value of all zeros. The condition ID will be the condition associated with outcome slots A, B, and C. We'll skip over the partition for now and go to the amount. So the amount, we will pass in all 100 units of T1 that the primary account holds and has approved the conditional tokens to use as collateral. Returning to this partition argument, you can see that it is an array of uints. It is actually an array of index sets, which we have discussed earlier. These index sets represent a subset of the outcome slots associated with the condition ID that was passed in here. What the word partition is being used here for is the fact that we are trying to partition the set of outcome slots for this condition with this parameter. So we are giving index sets that partition the outcome slots A, B, and C. One such partition that is noted here is the partition with a set of just A and a set of B and C. The index set for the outcome collection with only outcome slot A, as noted earlier, corresponds to the unsigned integer value of 1. So we'll supply this as the first element in this array. The index set value of 6 corresponds to a set of indices 1 and 2, which refer to the outcome slots B and C. We'll supply this as a second element of the partition. With this, we have completely specified how to do a split position from a collateral token. So we'll run this transaction and see what it does. Once the transaction is finished mining, assuming there are no reversions which happened, you'll see that the conditional token's state has changed, as well as the state of the account balances for token T1. So if we check the allowance that we just set for the conditional tokens, we can see that the allowance has changed in order to reflect that the conditional tokens used up that balance, and now it is at 0. Similarly, if we check the balance of the original account holder, we'll find that the balance of the account holder's T1 has been drained to 0 as well. This account has been moved to the conditional tokens contract. So in fact, if we check the balance of the conditional tokens, we'll see that the conditional tokens now has 100 units of T1 as a result of the split position call we have just transacted with. Running split position, however, has generated stake in a number of position IDs, or alternatively, you could say it has created new conditional tokens or outcome tokens. These newly minted tokens are assigned to the account which did the split position operation. In this case, we ask for the balance of the primary account, and we pass in the position ID for token T1 under the circumstance that either B or C occurs. We'll see that we have 100 units of this conditional token associated with that account in that position ID. Similarly, if we pass in the position ID for T1 under the circumstance that A occurs, we'll also see 100 units of this conditional token. This is a direct result of the call to the split position done earlier, in which we passed in T1 as the collateral token. We did a split from the 0 or the root collection ID. We pass in the condition ID associated with these outcome slots A, B, and C, as well as a partition containing the index sets associated with the collection IDs that form these positions. Note that we don't have any stake in the position ID that is backed by T2, so we check the balance of the primary account associated with that position ID, we will get 0. We take a look at this diagram in the developer guide. We can see a number of examples of valid and invalid splits. In this diagram, the $sign represents some collateral token, so just some ERC20 token. The split we just performed basically took some amount of this collateral token and turned it into conditional tokens, similar to how is diagrammed here. In this diagram, we see that the token has been split to a position that pays out when B occurs and the position that pays out when A or C occurs. This is similar to the transaction we just did, in which we split to a position that pays out when A occurs and a position where B or C occurs. We can also find the diagram of positions that are possible from two conditions and a single collateral token in the developer docs. In the transaction we've done, we had value in T1, and we took that value and split it into value in T1 under a condition that A occurs and value in T1 under a condition that B or C occurs. Splitting and merging are of course subject to certain rules to make sure that positions are properly backed and the conditional tokens contract doesn't create stake in positions that aren't backed by collateral. Looking at this graph of positions, you may notice that there is a second layer of positions here. It's tied very closely to the parent collection ID parameter. When we passed in 0 as the parent collection ID, what we are telling the contract is we would like to start from the root collection, or the collateral token directly. If we were to do a split position to reach these deeper positions, we may have passed the collection ID associated with one of these positions instead. Before I move to one of the second layer positions, however, I do want to note another split that is possible via split position. If you look in this diagram, you can see that the position that pays out when B or C occurs can actually be split into a position that pays out when B occurs and a position that pays out when C occurs. Since we have value in a position that pays out when B or C occurs, we can actually make this transaction now in the current state of the conditional tokens on our development chain. To do this, we will keep the collateral token the same to kind of stay within the position graph associated with collateral token 1. We will also keep the parent collection ID the same. The parent collection ID can be roughly thought of as the next level up. We'll keep the condition ID the same as well because that is the condition that outcome collections containing only B and only C share. The change that occurs here is in the partition. We want to figure out the index set values for only B and only C. With the process noted earlier, we can find those values. For example, the index set for the outcome collection containing only B is 2, and the index set for the outcome collection containing only C is 4. Since we are trying to split the position that pays out when B or C occurs into separate positions that pay out when B occurs and when C occurs, we'll pass in the partition containing the index sets corresponding to only B and only C. Since this does not cover all of the outcome slots in the condition, the split will actually look for value in the position B or C instead of try to get value from one level up, or in this case, from the collateral token. Finally, we have to determine some amount to split. This amount, since it is coming from a position in the conditional tokens instead of outside the conditional tokens as collateral, will be burned, and the same amount in the split targets will be minted. Since we have 100 in position B or C, let's see what happens when we split 30 of B or C into positions B and position C. Now when we ask the conditional tokens for the amount the primary account holds in the position that pays out in T1 under a circumstance that B or C occurs, we'll see that it's 70 instead of 100. As discussed earlier, 30 of this has been burnt and moved into positions that pay out when B occurs and position that pays out when C occurs. I'll leave deriving the collection ID for those positions and the position IDs for those positions up as an exercise. But you can verify that the primary account holds 30 units of conditional tokens in those positions. Note also that this split did not affect the amount of conditional tokens that the account is holding for the other position that we got conditional tokens in the first split. So if we check that, we would still have 100 units in that position. Now we've been supplying zeros as our parent collection ID this whole time. What this means is that we're only talking about a first level of positions. So if we look at the docs, when supplying zeros as the parent collection ID, we're generally working within this first layer of positions. However, another important feature of the conditional tokens is the ability to combine many different conditions in a single position. For example, I might have started out with 100 units of T1. I've split to 100 units of A, 100 units of B or C, and then I split 30 of those B or C to B and C, so now I have 100 units of A, 30 of B, 30 of C, and 70 of B or C. Now if I wanted to go deeper by splitting through another condition, perhaps a condition that has different outcome slots like low and high, I could do so and reach these positions down here. However, I could have also started out with token 1, split through the other condition first to get tokens in low and high, and then split the low token to, for example, these tokens here, and I would still reach the same position. That is to say, no matter what path I took to get to this position, as long as all of the moves I made so far were valid, this position is fungible. We can actually see this phenomenon reflected in the ID structure of the outcome collections. So let's look at the Git collection ID calculator. Originally, we specified zeros as the parent collection ID. This is to reflect that we're deriving IDs for positions in the first level of the position graph. We can instead, however, get collection IDs on the second level of the position graph by specifying a collection ID from the first level as the parent collection ID. So let's say we specify the collection ID for the collection of outcome slot A by itself as the parent collection ID. Then we specify the condition ID for the other condition, the second condition that we prepared, which has two outcome slots, low and high. Finally, we specify an index set that represents the index set for only the outcome slot high. So we might end up with a position that you can colloquially call A and high. It is the position that pays out in token T1 if both A occurs and high occurs. So to reiterate, we get the collection ID for the outcome collection containing outcome slot A and use it as the parent collection ID. You get the condition ID for the outcome collection we are combining this collection with. Finally, we get the index set associated with the collection of only high, which is 2. I'll make a note of this collection ID as the collection ID for A and high. Similarly, I'll find the collection ID that is associated with A and low by using the index set associated with the outcome collection containing only low, which is 1, while keeping the parent collection ID, the collection ID associated with the outcome collection containing A, and the condition ID of the outcome collection we are appending, which is just low. Now, I mentioned that it didn't matter which order you combined these outcome collection IDs in, and that because of this property, deeper positions in the position graph are fungible no matter what path you took to reach them. We can see this by providing for the parent collection ID instead of the collection ID for the outcome collection containing A, we provide the collection ID for the outcome collection containing high. And instead of the condition ID for low and high, we use the condition ID for A, B, and C. And we provide the index set associated with the outcome collection containing only A, which is just 1. And the result from this calculation, we can compare it with the result we got earlier from the other direction and see that we have indeed generated the same collection ID for A and high. Similar to earlier, we can use the get position ID calculator on the contract to figure out position IDs associated with these outcome collections that pay out given one of the collateral tokens. So for example, the position ID that pays out in token T1 when both A and high occurs can be gotten by putting the T1 token address as the collateral token and putting the A and high collection ID as the collection ID. Feel free to try this with different collateral tokens and collection IDs. Now we will return to split position in order to create a stake in these deeper positions. Recall earlier that we have 100 stake in a position that pays out in token T1 when A occurs. You can further split this to a position that pays out in T1 when A occurs and high occurs on the other condition, and 100 units in stake in the position that pays out in T1 when A occurs and low occurs in the other position. On the position graph in the documentation, you could see this as a split going from this node in the position graph down to these two nodes in the position graph. In the valid splits diagram in the next section, this operation we are planning to perform is similar to this part of the diagram, where stake in a position that pays out when A or B occurs gets split into stake in a position where A or B occurs and high occurs on a different condition, and A or B occurs and low occurs on a different condition. In our case, it's not A or B, but just A. So let's return to split position, where for the collateral token, we will leave T1's address as the input parameter, but instead of zeros as the parent collection ID, we will pass in the parent collection ID for outcome A. Now the condition ID is also different. It is the ID of the second condition we have prepared. In these diagrams, this condition is represented by a solid blue arrow. Our partition is going to consist of the index sets that partition these two outcome slots associated with this condition. However, there's only one such partition that is possible with two outcome slots. It is a partition containing the index sets associated with only low and only high as its members, so 1 and 2. Finally, we have to specify an amount to split. Recall that we have 100 units in the position that pays out in T1 under the circumstance that A occurs. Since we'll be burning from this position, we have to pick an amount less than 100 to burn in order to generate stake in the positions that pay out in T1 when A and high occurs, and the position that pays out in T1 when A and low occurs. Here I'll split 40 units of position A. Once this transaction has been mined, the transactor's balance in the position that pays out in T1 when A occurs which has this position ID, has been reduced by 40 to 60. On the other hand, the transactor now has 40 newly minted conditional tokens in these deeper positions. So if we check A and high, you see 40 tokens, and similarly for the position that's associated with A and low, you see 40 tokens. The split position method has a corresponding inverse called merge positions. Merge positions actually does basically the inverse of split positions. If an account acquires conditional tokens as a result of a split, it can also rewind that split by doing merge positions. If an account gets conditional tokens any other way, as long as the amounts it has in its inventory could be the result of a split, it can either merge those conditional tokens back into conditional tokens at a shallower level in the position graph, or it can release collateral backing those positions if merging to the root level. First, let's merge some conditional tokens representing A and conditional tokens representing B or C back into the collateral T1 backing those positions. To recall, our primary account has 70 units of conditional tokens in the position that pays out when B or C occurs, and 60 units of conditional tokens in the position that pays out when A occurs. That means we can merge 60 units each of these conditional tokens back into collateral. To do this, supply the address of token T1 as the collateral token parameter in the merge positions method. Put all zeros as the parent collection ID because we're merging to the root level in this case. Here the condition ID is the condition associated with the outcome slots we are merging. The partition will be the index set values corresponding to B or C and to A. So 6 and 1. And finally, let's merge 60 units of this back to collateral. Once the transaction has mined, you'll see that the conditional tokens contract has relinquished 60 units of its balance in token T1. So now it only has 40 units, whereas the primary account making the transactions has recovered 60 units of the token T1. So it now has 60 units of T1 in its balance again. We can also see 60 units of conditional tokens have been burnt in both the B or C position, which used to contain 70 units but now contains 10 units, and the A position, which used to contain 60 units but now has been completely burnt down to 0 units. Note that supplying the same parameters that we supplied to merge positions to split position would essentially undo that merge, or do the inverse of that operation that we just did. Except if you were to try and perform it, you shouldn't forget to set the allowance for the conditional tokens via the approve method. So having talked about splitting and merging positions on the conditional tokens contract, we can also now move to the aspect of conditional tokens that make it tokens, in the sense that you can send these tokens to another account or receive them from another account. So since the conditional tokens follow the ERC 1155 standard, there are certain methods defined on that standard that are intended for transferring tokens that have been implemented on the conditional tokens contract. These methods are safe transfer from and safe batch transfer from. You can read more about these methods on the ERC 1155 specification. Anyway, this primary account we've been working with has a number of conditional tokens with various position IDs. We can use safe transfer from or safe batch transfer from to transfer these conditional tokens to different accounts. Let's first start with the case where we're transferring to an externally owned account. We can check to see, for example, that the primary account at this point has 40 units of the conditional token that pays out in T1 when A occurs and low occurs. Let's transfer this conditional token to a different account. So in order to do that, we get this conditional token's position ID, or its ERC 1155 ID, and we supply it as the ID in the safe transfer from transaction. Since we have 40 of this token, let's send, say, 20 of the token to a different account. We also have to specify from and to. Notice that we can transfer from an account that is not our own. This is similar to the transfer from method available on the ERC20 token standard, in that an allowance has to be made for some account to transfer on behalf of some other account. However, in the case of ERC 1155, that allowance is set with the set approval for all method. For this particular transaction, we will not use set approval for all, since we'll be transferring from the account itself. So what I mean by that is we will transfer from this primary account, and we will make sure that this is the account that is executing the transaction. So this account is the message sender in the transaction. Let's say the second account in our list of accounts is the receiver. And so we will fill in the address of that account in the to field. Recall earlier that the ID is the position ID of the conditional tokens you're trying to transfer. Amount is the amount of tokens to be transferred. So in this case, 20 units. For a data field, we will ignore this for now and just specify empty bytes. It's important for the message sender of this transaction to be authorized to perform the transfer from. This is not the case. The transfer from would fail. So I'll just make sure that the sender of the transaction is the same as the owner of the conditional tokens. In this way, attempting this safe transfer from will succeed. Once the safe transfer from has been performed, the amount of the token that has been transferred from this account will be deducted from its balance. So if we check the balance of the token being transferred on this account, we'd see that it has been reduced from 40 to 20. Similarly, for the recipient account, or the account specified in the to field, if we check that account's balance, we'd see that the account balance has been increased from 0 to 20. Safe transfer from and safe batch transfer from are the primary methods in which these conditional tokens, or really any ERC 1155 token, gets moved around. These transfer functions are also the building blocks for exchanges. For example, an exchange contract which facilitates trades. I want to make a quick note about transferring to contract accounts. So notice here that this was a transfer from an externally owned account to another externally owned account. However, if the recipient's account address has code associated with it, or if it's a contract account, the contract receiving the tokens has to implement methods for receiving ERC 1155 tokens. To see this, we can create an instance of a contract and try to send it tokens, and we can see what it would take in order to make sure that these tokens are successfully returned. and we can see what it would take in order for these tokens to be successfully received. Let's start by creating a new Solidity source file. I'll call this source file hodlers.sol. First contract I'll write will be a naive hodler. I'll leave the implementation of this contract empty and compile this file. I will also deploy a naive hodler onto a chain. At the end of the deployed contracts list, we can obtain the naive hodler's address. Now let us attempt another safe transfer from. This time we'll be transferring from the second account to the naive hodler. So the to parameter will be the address of the naive hodler instance we just deployed. And the account that will be sending the 1155 tokens and from will be the second account. Let's send 5 units of this conditional token. Recall that this is the conditional token that pays out in T1 when A occurs and when low occurs. When we attempt to send this token, we'll find that the transaction will fail. The reason given by the contract, which comes from the Open Zeppelin implementation of ERC 1155, is that this is an attempt to transfer to a non-ERC 1155 receiver implementer. The error message that you might get on the official canonical conditional tokens contract might be different. However, the reason is essentially the same. Receivers of ERC 1155 tokens that are contracts must implement certain methods. In fact, if we look on the Open Zeppelin ERC 1155 contracts folder, we can find an ERC 1155 receiver contract, which essentially guides contract writers in writing a contract that can successfully receive ERC 1155 tokens. This contract can be found on GitHub under Open Zeppelin in Open Zeppelin's contracts. We can import it into Remix using the GitHub URL import method and specifying this path to the contract after the GitHub for the Open Zeppelin contracts. This path is under contracts, token, ERC 1155, and the contract name, which is ERC 1155 receiver.sol. When we try to compile this, Remix will automatically try to import this contract from GitHub. Once this contract has been imported, we can take a look at the contract that got loaded from GitHub. As you can see, the ERC 1155 receiver is an abstract contract that requires a couple of methods to be implemented. Specifically, the onERC 1155 received method and the onERC 1155 batch received method. This abstract contract also contains boilerplate used to set up the ERC 1155 receiver with respect to the ERC 165 standard, which is an introspection standard. This is a required method on the interface as well and helps contracts determine what sort of interfaces a specific contract implements. Let's create a hodler that inherits from the ERC 1155 receiver contract. We'll call this contract the ERC 1155 hodler contract, and we'll inherit from the ERC 1155 receiver abstract contract. The methods expected to be implemented on this contract come from the ERC 1155 receiver interface, which can be found in the IERC 1155 receiver source file. Let's copy the function signatures from this interface. Now these method declarations end in a semicolon. So in order to convert this into an implementation, remove the semicolon and add some braces. We'll do the same for the onERC 1155 batch received declaration. Turn it into an actual implementation. Now, if we look at the interface file for the IERC1155 receiver source file, we can see some documentation about how to implement these functions. In particular, the documentation states that to accept the transfer, this function must return, and then this bytes 4 of a hash of some string that contains a function signature. We also see the actual value of this, and also a note that states that this is just the function selector. What this means is that the method we are implementing may perform any sort of logic with the parameters passed in, but in order to tell the conditional tokens that yes, I would like to accept these conditional tokens, the contract must return this magic value. For the sake of simplicity, we'll just return this magic value. So there are sort of 3 ways hinted at here that we can do this. First off, we can use this expression for the function selector. This expression explicitly lays out the input parameters for the hash function, in that we're just taking the first 4 bytes of that result of the hash. So first way is to return something like that. Another way is to return this value. As you can see, the expression specified here is a constant expression, so it's always going to evaluate to this constant. So another way to mark a transfer as acceptable is to return this value directly. Finally, the documentation notes that this value is the function's own function selector. There's actually a way in Solidity to get a function's selector if we have an expression that refers to an instance of this contract, the ERC1155 hodler contract, or an instance of the ERC1155 receiver, or even an instance of the interface, then we could figure out the function selectors for the functions on that instance using the following syntax. So first, let's get an instance of the ERC1155 hodler. An instance can be found simply by providing this. This is a keyword that refers to the contract instance itself as it is executing this method. This has the type ERC1155 hodler. We can use this dot on ERC1155 received in order to refer to the on ERC1155 received method. One common way of using methods on contract instances that you've probably encountered is via a method dispatch. This is done with parentheses, and then you supply arguments to the method. However, this is not what we're going to do here. Instead, we are going to look for properties of this method. In particular, there is a selector property of the on ERC1155 received method. This selector property is exactly the bytes 4 expression here that calculates the selector value, as well as this value which already has been calculated. All of these ways of specifying that an ERC1155 token should be received works. So you may pick whichever one strikes your fancy. The situation is similar with on ERC1155 batch received. However, note that this is a different method from on ERC1155 received, so its selector value is actually different. Be aware of that and do not copy the contents of the on ERC1155 received method to the batch received method, because the function selector is different, and so the magic value necessary in order to indicate that a transfer should be received is different. On ERC1155 hodler, I'm going to write that this hodler just accepts all token transfers to it. We will compile this source file, Also, don't forget to specify on newer Solidity versions that you're actually overriding declarations from the interface with the override keyword. Once you recompiled the hodler's source file again, you can deploy an instance of the ERC1155 hodler. This time, use the ERC1155 hodler instance address as the recipient of the transfer from, and try this transaction. This transaction succeeds because the ERC1155 hodler contract implements the ERC1155 receiver interface in a way that has it accepting really any ERC1155 token. You can also check to see that the balance of the conditional tokens that were sent on the second account has been reduced from 20 to 15. Because the first call to transfer 5 units of this conditional token to the naive hodler contract instance failed, but the second call to transfer 5 units to this ERC1155 hodler contract succeeded. You can also check the ERC1155 hodler's accounts balance for the conditional token that was sent. And as expected, it's 5 because it received 5 tokens. Also want to briefly talk about the data field that we sort of skipped over discussing earlier. We had passed empty bytes into the data field, but in fact the data field can contain any number of bytes, and one use case for this data field is to actually put call data in here for contracts programmed to receive ERC1155 tokens. For example, we might have written a contract that should react to receiving ERC1155 tokens in a specific manner, maybe by checking accounts or something like that. In that case, the data in the data field that was supplied to safe transfer from would actually be forwarded to the receiving contract in the data parameter in the corresponding reception method. Reacting to receiving certain ERC1155 tokens, a contract might decide to parse this data out in some manner and use it somehow. Contrast this with the way contracts typically handle ERC20 tokens. With ERC20, contracts often expect users to approve an allowance for the contract's use. Then users would call a method on the contract which pulls the ERC20 from the user into the contract's inventory and do accounting or actions after pulling that amount. ERC1155 still supports this old pattern of first having the user approve the contract before having the contract pull ERC1155 tokens from a user through the set approval for all functionality. However, instead of having the user make 2 contract calls, one to the conditional tokens to set approval for all and another to the contract which handles the logic, a contract writer can instead write the on ERC1155 received and on ERC1155 batch received methods to directly react to receiving ERC1155 tokens and performing actions as a reaction to this reception, where the actions can be further specified through this data parameter. Alright, before I go further, I just want to make a quick note that my computer crashed so that all of the values that I had for IDs and account numbers were erased. So I basically replicated the actions up till now with a different set of accounts, and so all of my IDs here have changed, but hopefully this is still followable. Anyway, the last aspect of the conditional tokens that I want to talk about is reporting the results of conditions and redeeming positions. So far, we've talked about conditional tokens as if they had a value denominated in some backing ERC20 token under some circumstance where the outcome collection for the position is fulfilled. So for example, if I had a conditional token with this position ID that indicated that it is worth some amount of the T1 token when outcome B or C occurs, then when the oracle for the condition submits a result and B or C is the outcome that receives the payout for the condition, conditional tokens with this position ID can be redeemed for its backing collateral token. So first, let's look at the first condition we have prepared with 3 outcome slots, where we have set the oracle to the second account in the accounts list. And the question ID for this condition is the bytes 32 representation of 1. So 0x00000001 at the end. In order to resolve this condition, we use the method report payouts. Report payouts takes 2 parameters, the question ID and a payouts array. When an account makes a call to this method, the account calling this method, or the message sender, is assumed to be the oracle for the condition being reported on. And the length of the payouts array is assumed to be the outcome slot count. If these parameters are wrong, the conditional tokens contract will not find the prepared condition to resolve. So for example, let's say we have the question ID right, but instead of 3 values in the payouts array, we supplied 2. The report of the payouts for this condition would not work. So let's say the oracle is prepared to report the payouts for a condition. Well, what does that mean? For example, the question associated with a condition might be which one of 3 outcomes has occurred, A, B, or C. So once resolution occurs, it might be expected that one of the outcome slots should receive all of the payout for that condition. As mentioned earlier, the payouts array should have 3 elements, where each element represents the payout associated with an outcome slot. So let's say the outcome B occurs, which is the second outcome slot. In order to express that B should receive all of the payout associated with conditional tokens that depend on this condition, the oracle account would have to report a payouts array of 0, 1, 0, where the zeros indicate that the first and third outcome slots should receive no payout, and the 1 in the payouts array indicates that the second outcome slot should receive 1 out of 1 of the payout, or all of the payout. So we make this from the associated oracle account for this condition. We will have successfully reported the results of this condition, which means that conditional tokens that depend on this condition can now use the redemption functionality. In order to redeem conditional tokens, we need to use another method, the redeem positions method. The parameters for redeem positions look similar to the parameters for split and merge positions. You have to indicate a collateral token, there's a parent collection ID, a condition ID, and index sets that you would have to provide. There are a couple of differences between redeem positions parameters and split and merge positions parameters. First off, note that index sets is not called partition. That is because the index sets provided to redeem positions do not have to actually partition the outcome slots of the condition. More precisely, they do not have to be disjoint sets. For example, if you're holding B or C and only B and only C, you can pass in all three index sets into this array and redeem the conditional tokens associated with these index sets. The other difference is that there is no amount. That's because redeem positions will automatically redeem all of the available balance that you have of conditional tokens in a given position. The parent collection ID is there so that we can redeem to shallower positions instead of directly to collateral. In the documentation for redeeming positions, we have a chart that illustrates what redemptions are possible given an Oracle's report. For example, the Oracle report that we had submitted earlier, which allocates 100% of the payout to the second outcome slot B, allows for these sorts of redemptions to occur. For example, we can take the conditional token that pays out when only B occurs and redeem that for the same amount of collateral token. Similarly, we can take an amount of the token that pays out when A or B occurs and redeem that for the same amount of collateral token. However, conditional tokens on a deeper layer containing this condition can be redeemed to conditional tokens on a shallower level. So let's try a few redemptions. Since the first account has a number of conditional tokens, we'll start by trying to redeem some of the first collateral token backed positions on that account. Recall that after all of the transactions that we've made, this account has 10 units of token T1 when B or C occurs, and 0 units of T1 when A occurs. Also note that before we do anything, that the first account also has 60 units of T1. So the act of redeeming should turn the 10 units of T1 under a circumstance that B or C occurs to just 10 units of T1. To do this, we go to redeem positions. We supply the address of the first collateral token for the collateral token. Put in zeros for the parent collection ID because we are redeeming to the root or redeeming to collateral token. We'll use the condition ID associated with the A, B, and C condition, and we'll pass in the B or C index set as the only index set in the index sets array. So recall that the value for the index set representing B or C is 6. Executing this transaction, we'll see as a result that we won't have any more T1 under the condition that B or C occurs. So all of those conditional tokens have been burnt. Also, 10 units of T1 has been released from the conditional tokens contract to the redeemer, who now has 70 units of the T1 token instead of 60. Recall way earlier as one of our splits, we took T1 B or C and split it into T1 B and T1 C. And so we did that with 30 units of those conditional tokens. So in fact, if you look in the account for T1, you will see that the first account has 30 units of T1 under a condition that only B occurs, and 30 units of T1 under the condition that only C occurs. Since we did not provide the index sets related to these conditional tokens in our redeem operation, those account balances remained untouched. However, it is possible to redeem T1 under the condition that only B occurs for T1, since the Oracle reported that the outcome slot B should receive all of the payout. To do this, we keep the collateral token the same, it's T1's address. We keep the parent collection ID the same, it's all zeros. And we keep the condition ID for the A, B, and C outcome slots. However, instead of the index set for B or C, we supply the index set for just B, which is the value 2. We can also supply the index set that represents only C, which is 4. This means that the conditional tokens at that position will also be burnt to be redeemed. However, since the outcome slot C is supposed to receive none of the payout, all 30 units of the C token will be redeemed for 0 T1, so no tokens at all. In total, this transaction should burn all of the tokens in B and C while returning 30 units of collateral to the redeemer. So with this, we see that both B and C have 0 balance left, while the 30 units of B got converted into 30 units of collateral, meaning that the primary account now has all 100 of its original collateral back. You may also remember that this account has value in deeper positions, namely the A and high position and the A and low position. Since the outcome slot A does not receive any of the payout, these positions can be redeemed. But if you take a look at A and high, while you can redeem that to high, no matter how much you choose to redeem of A and high to high, you're going to get 0 high tokens. This is because the payout for A is 0. So let's, for example, recall that our primary account has 40 of A and high, and we can try to redeem this by providing the collection ID for high as the parent collection ID. So this is sort of the outcome collection that you are redeeming to. The condition ID remains the condition ID for the A, B, and C condition, and the index sets that we're redeeming is just the index set of A, which is 1. So performing this transaction, we essentially burn the account's balance of A and high, and because A is not allocated any of the payout for the A, B, and C condition, the primary account's conditional token balance of T1 high has also not been increased from 0. Now let's try reporting the result of the other condition. So make sure that you're transacting from the Oracle account associated with the second condition. Use the correct question ID as the question ID parameter in report payouts. And the supplied payouts array is going to have 2 elements to match the number of outcome slots in the condition. Now, if you were reporting for a scalar market, for example, it may be that you want to have the payouts for the different conditional tokens associated with this condition not be all or nothing. For example, maybe you'd want the low token to receive 25% of the payout and the high token to receive 75% of the payout. One way to do this is to supply the values 1 and 3 as the payout array. What this means is that amounts of the first conditional token can be redeemed for 1/4 of that amount, and amounts of the second conditional token, or the high conditional token, is redeemable for 3/4 of that amount. You don't have to use 1 and 3. You can also specify, for example, 25/75. And that would make sure that the low conditional tokens get 25 out of 100 or 25%, and the high conditional tokens get paid out at a rate of 75% or 75 out of 100. You could really use any numbers in the payout array, and the contract will consider them to be numerators and their sum to be the denominators for the payouts. So let's submit a payout report of 1/4 and 3/4. Now recall earlier that our primary account also had conditional tokens in A and low. To be precise, our primary account had 20 of these conditional tokens. Now while I demonstrated redeeming through the first condition earlier, we can actually also redeem through any of the conditions contained in that position in any order, which means we can redeem through the second condition, the low-high condition. In this case, we can redeem the A and low conditional token to the only A conditional token. In order to do this, we go back to our redeem positions. We keep the collateral token the same. However, for the parent collection ID, we want the only A collection ID. Also, instead of the A, B, and C condition, we are redeeming through the second condition, or the low and high condition. Finally, the index set of the low outcome slot is 1. So we'll supply just that index set to the array of index sets that we are trying to redeem. So making sure that the primary account's doing the transaction, if we perform this redemption, we'll find that the balance of this account's A and low conditional tokens has been burnt down to 0. Now recall that low is redeemable for a quarter of the original amount. So the original amount was 20 A and low, and the payout rate for low meant that the redemption left us with 5 units of only A. So if we check the balance for that position, we should find that we indeed have 5 units of that conditional token. Anyway, this concludes a tour of the conditional tokens contract. Hopefully you found this guide helpful. Peace!